So hello everyone. So today we'll be discussing about gaseous state. Gaseous state is a very important topic for IIT JEE and NEET chemistry. Also, it is a very fundamental topic to understand the basic physical chemistry. Okay. So before studying gaseous state, we need to know about the states of matter, right? So how many states are possible for matter? So states. We can categorize states into two main categories, right? One is your physical states and other one is your chemical states. Now chemical states can be also divided into two categories. One is like pure state, that is the pure chemical form of any compound. Another is mixture. And physical states can be further divided into 5 categories. One is gas, then liquid, then solid, then plasma, and fifth one is Bose-Einstein condensate, right? So in this chapter we will be discussing about the gaseous state, right? So further, gas can be categorized into two categories. One is your ideal gas and real gas. So before starting gaseous state, we need to know about the variables that defines a state of a gas. So the variables that defines the state of a gas, right? So what are they? They are like pressure, temperature, volume, number of moles, right? So we'll be discussing all the variables one by one, and the most important thing is to know about their units and their interconversions, because that is very important for solving numerical problems, right? So now coming to pressure, right? Pressure units we'll be talking about. So what is the SI unit? So SI unit is Pascal. And what is Pascal? Pascal is basically 1 Newton per meter square, right? Then 1 bar is also unit of pressure, and that is related to Pascal in such a way that 1 bar is equal to 10 to the power 5 Pascal, right? So bar is a larger unit. Then 1 atm is approximately equal to 1 bar, right? But if I take precise value, then 1 atm is equal to 1.013 bar, right? So I used to remember it like that. That is 1, and A is looking like 0, right? And T looks like 1, and AM looks like 3. So this is how I used to remember that 1 ATM is equal to 1.013 bar. It's a little bit silly, I know, but you can remember like this way. Okay, so if I take much further uh, precise value, then 1 ATM is equal to actually 0.1325 bar. Okay, but for numerical problems, if you take 1 ATM is equal to 1.013 bar, that is totally sufficient. Okay, so if I convert now 1 ATM to Pascal, then it will be 101325 Pascal, right? Because I have multiplied by 10 to the power 5. Okay, again 1 ATM is related to the column pressure of mercury, right? So 1 ATM is equal to 760 mm mercury pressure, right? And so this is equal to 76 centimeter of mercury pressure, right? Okay, now coming to volume. Now for ideal gas, ideal gas the volume of gas, I mean the volume of the gas molecules, I want to say volume of gas molecules. If I write molecules, that is actually less than volume of the container. Okay, so what I can write is that V free means that is not occupied. I mean V free means what I want to say is that V container minus V actual volume of the gas. Okay, this is so for ideal gas, V free is equal, almost equal I can say, to V container. Okay, because for ideal gas the rule is that the gas volume, the actual gas volume must be very low than the container volume where it is kept. Okay, now we are coming to the unit. What is the unit? So unit is, we all know SI unit is meter cube, that is the unit of volume, and 1 liter, that is actually 1 decimeter cube, the relation, and 1 ml, that is 1 centimeter cube. Okay, now coming to N. N is number of moles of the gas molecules. How N is defined? N is equal to mass of the gas by the molar mass. Okay, and now coming to the temperature, that is actually moles. Okay, and for the temperature, that is unit is Kelvin. Okay, now coming to ideal gas. Ideal gas. Ideal gas. So for ideal gas, what is the gas equation? That is PV is equal to nRT, where I already told, है ना? P is equal to pressure of the gas, V is equal to volume of the gas, N is equal to number of moles of the gas, and R is universal gas constant, and T is the temperature. Okay, so what we can see from here is that, what I can say from this equation, can I say PV by NT is equal to R, which is constant, as I told that R is universal gas constant. Okay, now let's talk something about R. Okay, the SI unit of R is mole inverse Kelvin inverse. Now if I want to change it to joule per mole per Kelvin, then what will be? It will be 8.314, है ना? Pascal per meter cube is joule. Okay, why? Because it is because this, you can see, this is pressure times volume, right? So pressure time volumes is equal to energy. Now you will ask why it is so. Let's derive for this. Okay, so pressure is what? Pressure is force upon area, yes, and volume, what we can see, volume, what we can write, is area into distance, kind of, है ना? Like, what will be the volume of this? This will be area of this and to this distance, yes or not? Okay, so if now I multiply P cross V, that will be what? Force upon area into distance, so that will be force into distance, so that will be energy. Okay, so that's why the Pascal meter cube reduced to joule. Okay, you must read this in your physics. Okay, so now there are other units of R also, that is R is equal to 0.082 atm liter Kelvin inverse mole inverse. Okay, or we can tell is like 0.083 bar liter Kelvin inverse mole inverse. Now what is the important thing is that for numerical purpose you need to remember these values with the units, because in numerical problems there will be conversions, you may have to use the conversions. Okay, so for that you need to remember these things. Okay, so now where we were we already derived that PV by NT, that is actually constant. So let's say I have two states of gas. State one is defined by a P1 pressure, V1 volume, N1 moles, and T1 temperature. Okay, and state 2 is defined by P2 pressure, V2 volume, N2 moles, and T2 temperature. Then for this, what will be the ideal gas equation? P1 V1 will be N1 R T1, and for this what will be P2 V2 is equal to N2 R T2. Now from this what we can derive is that P1 upon V1 divided by N1 T1, that is actually R, and from here what you can derive is that P2 V2 upon N2 T2, that is actually R. So we can see that both are now same. So if I equate these two equations, what I will get? I'll get P1 V1 upon N1 T1, that is actually equal to P2 V2 upon N2 T2. Okay, so this is one of the most important equations you have to use in your gaseous states numericals. Okay, this is the mother equation. Okay, from this equation we will derive many things, but this is one of the most important equations you need to remember. Okay, now in gaseous state you must be remember that there are many laws like Boyle's law, Charles law, Gay-Lussac's law, Avogadro's law. Now from this equation we can actually define all the laws. Okay, so let's start. Okay, so let's say at constant moles and temperature, what the equation will be? The equation will reduce to P1 V1 is equal to P2 V2, right? Or what I can say is that PV is equal to constant, right? Or what I can say that P is inversely proportional to volume. Okay, so what is this? This is called Boyle's law. Okay, now let's say at constant moles and pressure. Okay, what will be constant mole and pressure? So it will be V1 by T1 is equal to V2 by T2, or what I can say is that V by T is equal to constant, right? Or what I can say is that V proportional to T, right? So what is this? This is called Charles law. Okay, now let's say at constant moles and volume, what will be? P1 by T1 will be P2 by T2. Or what I can say is that P by T is constant, right? Or what I can say is that pressure is proportional to temperature. So if I increasing the pressure, proportionally the temperature will increase. This is actually law of Gay-Lussac. Gay-Lussac's law. This is Gay-Lussac's law. Okay. Now, what parameter we can take constant is that now we can take at constant temperature and pressure. Okay. So now if we take constant temperature and pressure, then what will be? Constant temperature and pressure. Then we can say is that V1 by N1 is equal to V2 by N2, right? Or what we can say is that V upon N is equal to constant, right? Or I can say is that V proportional to N, right? Whose law this is? Yes, this is law of Avogadro's. This is Avogadro's law. This is Avogadro's law. So from this equation, you can remember all the laws, and you will not forget this. Okay. Now, what ideal gas equation says? PV is equal to nRT. Now, in sum of numericals, you will see that we need the relationship between molar mass and density. Okay. So what I am told is that relationship between molar mass and density. Okay, molar mass and density. So how we'll derive from this? So we know that PV is equal to nRT. Okay, so what I can do is that PV is equal to M by M RT. Now this is M is the mass of the gas, right? And what is capital M? This is the molar mass. Molar mass of the gas, right? So from here what you can derive is that PM is equal to M by VRT, right? Or what I can do is that PM is equal to DRT, right? Where D is the, this M is the molar mass, and D is the density. Okay, so this is the relationship between your molar mass and density. Okay, now how actually I have, when I was studying at that time, I made a trick to remember this. You can remember this by remembering it as dirty PM. Dirty PM. So PM is equal to DRT, right? So this is a silly thing, I know, but if you want to remember, you can remember by this. Okay, so from this equation, let's say again, if we have two states with, let's say, state 1 with having pressure P1, molar mass M1 and density D1 and temperature T1, and state 2 if we have pressure P2, molar mass of the gas is M2, density D2 and the temperature T2. Now you must be thinking that there I have told the states are defined by P, V, T, N. Now here again I am defining by molar mass, F density. How I can do that? Actually, we can interchange the variables also. Okay, so such as density. Okay, so we can derive other state of variables from other things, like for density. How we can derive density? Density is like mass, molar mass upon volume. Okay, so it is actually interrelated with your interrelated with your number of moles in that state. So these they are actually interrelated. Okay, so you can interchange between them when you are defining the states. Okay, so whatever. Now from these, what we can do is that now you can say that P1 M1 by D1 T1 is equal to P2 M2 by D2 T2. Okay, so this is the relation. This we may have to use when we are doing numerical problems. Okay, now coming to another thing, that is graphs. So graphs are also very important in gaseous state, because you will see that in gaseous state there are many laws, so there are many relationships, so we need to know their graphs also. Okay, so first graph we'll plot for your Boyle's law. Okay, sorry guys, Boyle's law. Boyle's law. Boyle's law. What it tells? It tells that P is inversely proportional to volume, right? So now if we plot P versus V, how this will be? This will be your like this, right? As this is a inverse relationship, right? But let's say if I plot what will plot? I plot here. Okay, if I plot P versus 1 by V, then it will be a straight line, right? Why? Because now this is your proportional relationship, right? Now coming to your second graph, that is Charles' law. That is Charles' law. What it tells? Charles' law tells that volume proportional to your temperature. So as temperature increases, the volume increases. So if I plot this, how this will be? Volume, temperature, this will be a proportional increase, right? And let's see the third thing. If I plot what law that was? Gay-Lussac's law. Gay-Lussac's law, right? That tells pressure is proportional to your temperature. So if I increase the temperature, the pressure of the gas will increase proportionally, right? So now if I plot pressure versus temperature, that will be this, right? So now Okay, these are done. Now, we need to know how to plot isobars, isobars, isotherms. Okay, so isobar means that your pressure will be constant. Pressure will be constant, right? And isotherm means temperature will be constant. Constant, right? So now, if I plot a graph between volume and temperature at constant pressure, so what this will be called? This will be called a isobar, right? Because the pressure is constant, right? So let's say I want to plot two graphs, I mean two curves. One graph that is depicting two states, right? One state is this, one state is this, right? This is actually two systems, I can say, not one state or something, right? Let's say this one is at P1 pressure, this one is at P2 pressure, and here is your temperature axis, this one is your volume axis, right? Now, can you tell me that what is the relationship between P1 and P2, right? So let's say if I draw a straight line here, let's say this is my point V1 and this is my temperature T1, right? And this is your volume V2, right? Now at T1, V1 is greater than V2, right? Now Boyle's law says what? P is inversely proportional to volume, right? So that means at constant temperature, the gas which has higher volume must have lower pressure, and at the same temperature, the gas which have lower volume must have higher pressure, right? So from this we can tell that P2 must be greater than P1, right? Okay, now coming to our next thing. Let's say I want to plot a graph between pressure and volume at constant temperature, right? So what this will be called now? This will be called isotherm, right? Because the temperature is constant. Isotherm, right? Isotherm. So now if I plot isotherms for different temperatures, let's say uh, like this, like this, and like this. Okay, so this was is for temperature T1, this one is for temperature T2, and this one is for temperature T3, right? And what is the x and y axis? X-axis is my volume and y-axis is my pressure, right? Now from this, can you similarly tell the relationship? What is the relationship? What is the relationship between T1, T2 and T3, right? Now similarly, let's do a straight line, right? So let's say this is pressure P1 and the corresponding volumes are V1, this is your V2, this is my V3, right? So at pressure P1, V3 is greater than V2 is greater than V1, yes or no, right? Now Charles' law says volume proportional to temperature, right? So what it means? It means that T3, not T3, V3 corresponding temperature is T1. T1 is greater than T2 is greater than T3, right? So this is the relation. Okay, now if I ask you, can you draw a graph between PV versus V? Can you do that? From ideal gas law, what we know? PV is equal to nRT, right? PV versus V. Now what you will see that PV versus V at what? At constant temperature and moles, right? So these things will have to be constant, otherwise you cannot plot this. If all things are varying, then it will be a 3 or 4 dimensional plots, right? Okay, whatever. So now can you plot this? Now let's see. So the graph is PV versus V, right? So at constant T and N, PV is equal to constant. That means it does not depend on any variable now, right? These things become constant. So if I am varying anything, there will be no variation, so it will be a constant line, right? Now can you explain why this is happening? I mean, can we understand this? Okay, so Boyle's law tells that P is inversely proportional to volume, right? So what it means is that as the volume is increasing, the pressure is decreasing such a way that their product always remain constant. So this is how these always remain constant over this range, right? So as volume is increasing, the pressure gets decreased. Okay, so similarly, if I ask you, can you plot PV versus P plot, right? So here similarly, if you see that PV is constant, right? So that means at constant T and N, right? So similarly there shouldn't be any change if I change the pressure. So there the graph again also will look like this. Okay, now if I ask you, can you plot log P versus log V at constant temperature? Can you plot this? So what do we know? We know that PV is equal to nRT, right? So we'll take log both sides. So log PV is equal to log nRT. Yes or not? So what we can say is that log P plus log V is equal to, now what at constant temperature, and then so now you see that these things now become constant as temperature is constant, R is universal gas constant, and I tell that N is constant. It is a closed system, that's why. Okay, so these things become constant. So can I write this as log C? C means constant. Okay, so this, so now I can tell it like I can write it like this, that log P is equal to log C minus log V. Okay, so this is actually Y is equal to mx plus C in this format. Okay, so now if I plot this, if I plot log P versus log V, right? So how that will be? Sorry, log V. So extreme. So sorry, I am. So basically, this is my C, and this is my mx, right? Where m is equal to -1. So there is a negative slope, right? And this is my intercept. Log C is my intercept. Okay. So here you will see that this is the intercept. So this is log C, and my slope is equal to -1. So this will be the plot, right? Okay, now these basics are done. Now if I ask you a question, can you answer this? The question is that a container can withstand a pressure of 12 atm. It is present at 1 atm and 27 degrees centigrade. At what temperature it will explode? So you try to do this, take your time, and you can pause the video, and if you want help you can see my solution, right? So okay, now if I see at the question, a container, right? So this is a closed container. So what I can see is that my number of moles and volume, this is constant, right? Constant. So what was the relation? That was P1 V1 by N1 T1, that was equal to P2 V2 by N2 T2, right? Now NV is constant, that means P1 by T1 is equal to P2 by T2, right? Now what it tells that the initial state was 1 atm and 27 degree centigrade. Now one thing to remember is that when you are solving these questions, always try to do in Kelvin, right? Not degree centigrade, because if you remember the ideal gas constant value R was in none of the R unit there was degree centigrade, all were is in Kelvin. If you remember this here, see, so all were in Kelvin, right? So I will request you to make a practice that always use the temperature in Kelvin when you are solving gaseous state or thermodynamics problems, right? So whatever. So what is your, my T1 is equal to 27 plus 273 Kelvin. So that is actually 300 Kelvin, right? And my P1 is 1 atm, right? So now what it tells that it can withstand a pressure of 12 atm, right? That means if the pressure exceeds 12 atm, it will explode. So now let's derive the, now P2 pressure is what, 12 atm, right? Now let's derive the temperature for 12 atm. I mean at what temperature it will attain 12 atm pressure, right? So if I put here the P1 is 1 atm and T1 is 300 Kelvin, P2 is 12 atm, then T2 will be what? So I can cancel that. T2 will be 3600 Kelvin. So this means if the temperature exceeds 3600 K, then it will explode, right? So this is the thing. And when you are solving these questions, try to associate the units with the values when you are solving this, okay? So this will also reduce your mistakes, or you can see that if I need to change the unit in the course of solving or not, okay? Okay, now coming to question 2, right? So the question says that if a gas is heated from 300 Kelvin to 900 Kelvin in an open container, so keep in mind that, okay? Then then calculate the fraction of the gas expelled out, okay? So give it a try, pause the video, and if you are having any problem, then you are most welcome to come and see the solution, okay? Okay, let's go to the solution now. Now what I have told is that this is a open container. That means this is a open system. Open system. That means it has volume constant and temperature and pressure constant, because it is in atmospheric pressure, right? Constant, right? So what was the equation? P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. Now volume and pressure are constant. That means N1 T1 is equal to N2 T2. Now from this relation, that N1 T1 is equal to N2 T2, you can see that as volume and pressure are constant, that means to keep these things constant, if temperature increases, then N must has to be decreased, and from this we will calculate how much N2 has decreased from its initial state, and from that we can calculate that how much fraction of gas is expelled out, okay? So let's try that. Initial state, that was N1, temperature was 300 K and it was N2 and temperature was 900 K. That means N1 is equal to 3N2, right? So that means N1 divided by N2 is equal to 3, right? So you can see that N2 is equal to N1 by 3, right? So you see that now 1/3 N1 fraction remains in the container, container now at 900K, right? That means N1 minus N1 by 3, that is your 2N1 by 3 expelled out, right? I hope you understand. If you have any doubt, you can ask me in the comment section. I will definitely help you. Okay, so now let's go to question 3. The question says, if the temperature is increased by 1 degree centigrade on increasing the pressure 0.4%, then what is the initial temperature? So give it a try, pause the video, and same as before, if you find it difficult, you are most welcome to see my solution. Okay, let's try. Okay, so let's start. So let's say let initial pressure is P1, initial temperature is T1, right? And let's say volume is V. Okay, so what is ideal gas equation? Ideal gas equation is PV is equal to nRT, right? So from here what we can see is that P is equal to nRT by V. Okay, or for this state what we can say is that P1 is equal to nRT1 by V, right? Now we will try to incorporate these conditions to equate the equation, right? So what it tells, if the temperature is increased by 1 degree centigrade, right? So at state 2, this was your state 1, right? State 2, what they did temperature T2 is equal to T1 plus 1. Okay, so they increased the temperature by 1 degree centigrade, right? And they what did they did to the pressure? The P2 becomes P1 plus 0.4% of P1, that is your P1 1 plus 4 upon 1000, right? So now what the equation of state will become? Equation of state will become that P1 1 plus 4 upon 4000 will be equal to your N R by V, right? T1 plus 1, right? Now this was your initial state, this was your final state, right? Now what we can do is that we can do 1 by 2, equation 1 by 2, right? What we'll get? We'll get P1 divided by P1 1 plus 4 upon 1000 is equal to NR T1 by V upon NR by V T1 plus 1, right? Or 1 upon 1 plus 4 upon 1000 will be equal to T1 by T1 plus 1, right? So what that will give? That will give me 1000, this 1000 goes there, 2004, 1004, yes, equal to T1 upon T1 plus 1, right? And from here what you get, 1000 of T1 plus 1000 is equal to 1004 T1, right? So what I'll get is this will goes there, so 10 to the power 3 is equal to 1004 minus 1000 T1, right? So 4 T1 equal to 1000, or I can say is that T1 is equal to 1000 upon 4, that is equal to 250 Kelvin. So the initial temperature was 250 Kelvin. I hope you understand this. Okay, so now we'll go to a different section of gaseous state, that is mixture of gases, right? Like what will be the properties, or how to determine the properties if we mix the gases, right? So till now you get to know that gas has different properties. What are the properties? Like moles, then volume, then pressure, right? Properties means the variables you want to say, right? Then temperature, already you know, we have discussed this already, okay? Then density, then molar mass, that is a M, okay? So now we can categorize these properties into two types, right? One is your additive properties, another is your non-additive properties. Additive properties are which properties that you can simply determine by addition, right? Like moles, right? Let's say you have gas A mixed with gas B. Now in the final state, the total moles will be moles of A plus moles of B, right? So moles is a additive property. Similarly, volume is also additive property, right? Non-additive properties like temperature. So temperature is not a non-additive property. Like if you mix gas A and B, and gas A is of temperature T1, gas B is of temperature T2, you cannot say that the final state will have a temperature of T1 plus T2, right? Can you say that? We can't, right? Okay, excuse me. Okay, then pressure. This is also non-additive property. Then density, then molar mass. So these are non-additive properties, right? So let's say gas A plus gas B was mixed to final state, right? So moles, these are additive properties, like gas A of mole N1, gas B of mole N2 are mixed. So in the final state, what will be the total mole? The total mole will be N1 plus N2, right? Now gas A of volume V1, gas 2 of volume V2 are mixed. Total volume will be V1 plus V2. Now pressure, initial pressure P1, sorry, gas A of pressure P1, gas B of pressure P2 are mixed. So total pressure will be not equal to P1 plus P2 because these are not additive properties. Now molar mass, gas A of M1, gas 2 of M2. Now if I final state molar mass, or if I say total molar mass in the final state, that will not be equal to M1 plus M2, right? Similarly, density, gas A has density of D1, gas B have density of D2. In the final state, total density, if I say, so that will not be equal to D1 plus D2, right? Okay. So if pressure is not an additive property, then if two gases are mixed, then how do we determine the pressure of a mixture, right? So this we will discuss now. So we'll discuss how to determine pressure of a gas mixture, right? Mixture, pressure of a gas mixture. Let's say this is the container where A is mixed with gas A and B are mixed, right? This is A, let's say these are B. Okay, so let's say pressure of gas A is PA and pressure of gas B is PB, right? So these are their initial pressures, right? When they are not get mixed, they will have some pressure, right? Some pure gas A, this will have some pressure. We have measured that, that is PA. And similarly of gas B, that is PB. Now these are not additive, so final pressure if I say, this is not equal to PA plus PB, right? But N is your additive property, like number of moles. So N final is Na, like number of moles of A plus number of moles of B, right? So now from ideal gas equation, how do you know? PV is equal to nRT, right? So my N will be PV upon RT, right? So in final, what you can write? In final is equal to PA VA upon RT, considering they are at similar same temperature, we can write VV upon RT, right? So what you can write, or let's say in final, how do we write that? P final, right? Let's say P final V final divided by RT is equal to 1 upon RT PA VA plus PV VV, right? So RT got cancel out, so I can write P final V final is equal to PA VA plus PB VB. Now let's say that when gas A was the pure gas A, let's say that has a volume of Va when they're not mixed, right? They are pure gas. Similarly, when gas B was in pure state, that has a volume of Vv, right? And when they are mixed, they get the volume A plus B, that let's say V final, right? Now what I am saying is that this volume are same, right? Let's say a gas was in 10-liter container, gas A. Similarly, gas B was also in a 10-liter container, and when they got mixed, they were mixed in a 10-liter container only. So that means what? Let's say VA is equal to VB is equal to V final, right? So then P final will be what? P final will be PA plus PB, right? Because V will get cancelled out from each side, and what we'll get? We'll get P final is equal to PA plus PB. This is called Dalton's law. Dalton's law, right? Now we have derived this, but this derivation has some conditions to make it satisfy this equation, right? So what is the conditions? Condition first is that the gas we have mixed must have to be ideal gas. Then only this equation will be valid. Two is that they must be non-reactive, right? So the gas we have mixed, they should not have react with each other, right? Third is temperature and volume has to be constant, right? That I have already told, that V final is equal VA and VB, and obviously pressure is related to your temperature, right? So in the final state, if you are increasing or decreasing your temperature, proportionally the pressure will get varied. So make this equation valid, the temperature in the whole process has to be constant, right? Okay, so okay, now I will describe Dalton's law, like what it actually says, right? So Dalton's law says, so what it says, total pressure is the sum of partial pressure of individual gases, right? So what was the equation? That P was equal to PA plus PB, right? So these are your partial pressures, right? This is your total pressure, okay. So if I write it in more general way, so I will write that, let's say gas mixture has in components, right? In number of individual gases, right? A mixture has, let's say a mixture has in number of individual gases, right? Then what will be the total pressure? Then P total will be equal to P1 plus P2 plus dot Pn, right? So that is actually the partial pressure of gas 1 plus partial pressure of gas 2 up to partial plus pressure of gas n, right? So look, how can write this is like summation of over pi, where I goes to 1 to n, p total. Okay, so this is your Dalton's law, right? Okay, so let's discuss a question, then the concepts will be more clear. Okay, are you ready? Okay. Okay, so I have not written much. I have only written the values we need. Okay, so what it says that oxygen is mixed with hydrogen. So oxygen of 3 moles is mixed with hydrogen of 2 moles, and in the whole process the volume was kept constant. The volume is 8.21 liters, and the temperature also kept constant. The temperature is 300 Kelvin. So you have to derive the P final, the final pressure of the system. Can you do that? Give it a try. Pause the video and give it a try, and come back to see the solution. Okay. Okay. So we all know the gas equation Pv is equal to nRT, right? So let's say we can write this P final into volume is given, that is 8.21 liters, is equal to n, right? So now n is in the final state, n is the sum of these two, because these two got mixed, right? So this much moles. Then R is, we all know. Now here, tell me which are isodius, I mean in which form isodius. So here I will use R in the unit of liter atm mole inverse Kelvin inverse, because here it is liter, here it is mole, right? So R in is liter atm mole inverse Kelvin inverse form, the value is 0.082, right? Liter atm mole inverse Kelvin inverse, right? And into the final temperature is how much? 300 Kelvin. So Kelvin cancelled out, mole cancelled out, liter cancelled out. So P final is how much? 5 into 0.082 into 300, that is atm, right? So atm divided by 8.21, right? So now we can solve this. So 5 cross, if I say 82, then I have to divide it by 1000, right? And here is 300. Now similarly, if I say 820, let's say 82 only, okay? So I have to, I'm approximating this, right? So this is atm. So this cancelled out. So this is approximately 15 atm, right? So my final pressure is 15 atm. Okay, now let's discuss question 2. Hopefully you understand this, right? So let's go to question 2. Okay, so the question says that ammonia, okay, this is gas, is reacted with HCl gas to give NH4Cl solid, right? Initially at T equal to 0, the moles of ammonia gas was 2 and the moles of HCl gas was 1, right? After the reaction, what will be the final pressure of the system, right? So give it a try, and I am always here to help you. Okay, so one hint is that pressure exerted by solid is equal to 0, right? So use that hint and try to solve this. Okay, so let's start. Hopefully you have solved, right? So what I can say, at t equal to t, where the reaction happened, then see here 1 mole of NH3 reacts with 1 mole of HCl to produce 1 mole of NH4Cl, right? So now if 1 mole of NH3 reacts with 1 HCl to form NH4Cl at the final state, the mole remaining of NH3 will be 1 and mole remaining of HCl would be 0 and 1 mole of NH4Cl will be generated, right? Generated, right? This is after reaction. Right? Now as this is solid, NH4Cl is solid, this will have negligible contribution. Okay, so now we can use our state of equation, that is PV is equal to nRT, to calculate the final pressure. The volume is given as 8.21 liters and the mole we have derived, that is 1 mole in the final state after reaction, and R is 0.082. Again we will use liter ATM unit, mole inverse, Kelvin inverse, and temperature is how much? 300 Kelvin. So Kelvin cancel out, mole cancel out, liter will get cancelled. So now pressure will be how much? 1 into 0.082 ATM into 300 divided by 8.21. So similarly it will get cancelled, a similar fashion here. So the remaining will be how much? 3 ATM, right? So the final pressure will be 3 ATM. Okay, now what we'll define? We'll define the mole fractions, right? And mole fractions, and we will make it relate to mole fractions relationship with partial pressure. Right? So let's say I have gas A and I have gas B and I have mixed them. Now I have mixture of gas A plus B, right? Okay, so here let's say here the moles of gas was Na, here the moles of gas was Nb, and now I have N, that is total moles, right? And here the pressure of gas A was Pa, the pressure of gas B was Pb, and here the total pressure is P, right? So N total N is equal to how much? Na plus Nb, right? And total pressure is how much? Total pressure is my P, right? That is Pa plus Pb, right? So these are my partial pressures, right? Now what is mole fraction? If I ask you what is the mole fraction of gas A in the mixture, you will tell that if I say the mole fraction of gas A. This A in the mixture. How do you tell? Mole fraction of A is that is defined by this symbol. A is equal to moles of A divided by total moles, that is Na plus Nb, right? Similarly, mole fraction of gas B will be how much? This Nb divided by Na plus Nb, right? This is the mole fraction. Now what I want to derive the relation, that is how the partial pressure of A is a function of mole fraction, right? This I want to derive. Okay, so how we'll do that? So okay, so now right, P is equal to what? P is equal to PA plus PB, right? So now PA is equal to how much? Because we know that state of the equation is PV is equal to nRT, right? Or P is equal to nRT by V. So for PA it will be nRT upon V if T and V are constant. Similarly, PB will be NB RT upon V, right? Or Na plus Nb into RT upon V, that is equal to your P, right? So now if I divide PA by P, that is what? Na RT upon V divided by Na plus Nb RT upon V, yes or not? See, this is PA and this is my P, right? So this upon this, so RT upon V will cancel out. This will Na by Na plus Nb. So this is none but the mole fraction. See this, so this is mole fraction of A, or what I can write, that is PA is equal to mole fraction of A into P, that is total pressure, the final pressure, right? And similarly I can write PB by P, that is equal to NB RT upon V divided by Na plus Nb RT upon V, that is Nb upon Na plus Nb, or PB is equal to mole fraction of B in the final state into P, or P final, right? So this is the relationship. Here I am telling you that we need to derive the relationship, right? PA or PB, so defining it as PI, right? PI as a function of this, right? So now this is the relationship we got, how they are related, right? So what will be the general form? So general form will be, if I say general form, so that will be Pi is equal to mole fraction of that gas in the final state into total pressure, or in the final pressure. Okay, right? Don't get afraid by these notations. Try to understand this only, right? So this is the partial gas, the partial pressure of the gas you want to determine, of gas of interest. Gas of interest I am writing, right? Interest. And this is the mole fraction of that gas in the mixture and P is your total pressure of the mixture, total pressure of the mixture, right? So if I tell you that I have mixed gas A plus B plus C, right? So I need to write, and the total pressure is P, moles of gas A is Na, moles of gas B is Nb, moles of gas B in Nc. I need to write partial pressure of A, partial pressure of B, and partial pressure of C as a function of their mole fraction. How will write that? Simply, that is Pi is equal to Xi into P, right? So Pa will be their mole fraction in the mixture into total pressure. Pb will be mole fraction in the mixture into total pressure. Pc will be mole fraction into total pressure, right? If I write that, so that will be Na divided by total number of moles, Na plus Nb plus Nc into P. This will be Nb divided by Na plus Nb plus Nc into P. This will be Nc divided by total number of moles into P, right? So this is how we can calculate. Okay, now let's do an interesting question, right? So we have a connected container, right? This is connected container, and here is a stopcock there, right? So one side it's contain a gas at 9 atm pressure and the volume is 5 liter, okay, and another side the gas is at 4 atm pressure and the volume is 10 liter, right? So don't go with the size, it should be larger, okay? So pardon me, okay, whatever. So after opening the stopcock, let's say stopcock is get opened, what will be the final pressure after opening the stopcock? What will be the final pressure that you need to calculate? So give it a try, and I'm always here, okay? So see here, the volume is not constant. Constant means here V final is different from their initial volumes. So here V final is how much? 5 liter plus 10 liter, right? 5 liter plus 10 liter, that is 15 liters, okay? Now see here, now I need to calculate what? P final, right? P final is how much? That is nRT upon V final, right? So you can see that V final we have calculated, but N final is basically moles of gas A plus moles of gas B, but here the moles of the gases are not given, so we need to calculate them. So how we'll calculate? For gas 1, let's say for gas 1 I am considering this as gas 1, right? So what is that? P1 V1 is equal to N1 RT1, let's say. So for that, what you can write is that P is how much? 9 atm cross 5 atm is equal to N1 into RT1, right? So my N1 is equal to 45 5 liter, that is, sorry, 5 liter. So liter ATM divided by RT. Instead of T1 we can consider only T, because the temperature is not changing, temperature is constant for the process. Okay, so for gas 2 similarly we can find out, right? So for gas 2, P2V2 is equal to N2RT, or P2 is how much? 4 ATM, right? And that is 10 liter, and say N2 into RT, or N2 is equal to 40 liter ATM by RT, right? Okay, so P final we can put here N1 plus N2, then how much? N1 plus N2 if I write, that is my 45 plus 40 divided by RT, this much liter ATM, right? So that is my 85, right? So 85 liter ATM divided by RT, this is my N. I multiply this by RT, that is this RT, and the final volume is my 15 liter. RT got cancel out, liter cancel out, so my answer will be how much? 85. So 60. So basically approximately I should be 5 6 7, this much ATM, right? So this will be my final pressure. So now what we have done, the partial pressure, sorry, the final pressure, and your mole fractions, right? So this is done, right? Partial pressure is done. Now what we have to do, we have to find the relation for molar mass of the mixture, right? So molar mass is also not a additive property, right? So how do we find the molar mass of a mixture? So molar mass of a gas mixture, right? Molar mass of a gas mixture. Generally in chemistry, how do we define molar mass? In chemistry generally moles equal to mass upon molar mass, or molar mass is equal to mass upon moles, right? So here similarly effective molar mass is equal to total mass upon total moles, right? So how do we find total mass? So let's say I have a two component system which is made by gas A plus gas B. Gas A has N1 moles, gas 2 has N2 moles, with molar mass M1 with molar mass M2, right? So then total mass of the system after mixing is equal to N1 M1 plus N2 M2, right? And total moles is total mole is equal to N1 plus N2, right? So effective molar mass will be equal to N1 M1 plus N2 M2 upon N1 plus N2. Right? So this is the formula for to find effective molar mass of a. Okay, now we can do a short exercise to understand this better. Let's say hydrogen and oxygen get mixed. Hydrogen has let's say this is of 1 mole and this is 1 mole get mixed. So find effective molar mass of the mixture, right? So how will do that? So we know that molar mass of hydrogen is what? 2 gram per mole, right? And molar mass of oxygen is 32 gram per mole, right? So given that, can you solve this? Give it a try and pause the video and see you after you solve it. Okay. Okay, so now effective molar mass is equal to effective molar mass is none but N1 is how much? 1 cross M1 is M of H2, so 2 plus 1 cross 32 divided by total moles 1 plus 1, so 2 34 by 2 17 gram per mole, right? Gram per mole. So basically here you have mole and here we have so 17 gram per mole is the answer. Okay, now next question. This is little bit interesting. Okay, the question says for air which is composed of mainly 17% N2 and 30% oxygen, find molar mass of the mixture. Okay, so give it a try. Okay, so M effective is equal to let's say see here okay, so N of N2 molar mass of N2 plus N of oxygen molar mass of oxygen divided by N of N2 plus N of oxygen. Okay, so let's say total moles is, let's say total moles of the mixture is 100, right? Then N of N2 will be how much? 70% of 100. So how much will be that? That will be 70 moles, right? And N of O2 will be how much then? 30 moles, right? And we know that molar mass of N2 is how much? 28 gram per mole, and mole of Oxygen, how much? 32 gram per mole. So putting all the values in the equation, what we'll get? M effective is equal to 70 moles cross multiplied by 28 gram per mole plus 30 moles 2 gram per mole divided by 100 moles. So moles cancel out, so that will be your 70 cross 28 16 6 190 plus 32 6 9 960 divided by 100 gram per mole. So that will be your how much? 0 2 9 2 divided by 100 gram per mole, or equal to 29.20 gram per mole, right? So this is how we can solve this. So from here we can find an interesting fact is that what? See, the effective molar mass is how much? 29.20, right? And molar mass of oxygen is 30 and molar mass of nitrogen is molar mass of oxygen is 32 and molar mass of nitrogen is 28. That means air is heavier than nitrogen gas, right? Pure nitrogen. But air is lighter than oxygen gas, right? Okay, so we have found the molar mass of a mixture. Now we need to find how to determine density of a mixture, right? Because density is also not additive property, so we need to find density of a mixture, right? Density of a mixture. So generally density is given by what formula? D is equal to mass upon volume, right? So here is the simple thing. How we find D mix will be D mix means density of the mixture will be total mass of the mixture divided by total volume of the mixture, right? So one thing you see that for the properties which are not additive in nature, in these cases we try to make these properties as a function of the properties which are additive, right? Like this, like you see the density of a mixture. Density of a mixture is not an additive property, but we have decomposed this to a function of mass of the mixture and the volume of the mixture. Now the mass of the mixture is additive property, right? And the volume of the mixture is also additive property. So by these we find the properties which are not additive, right? Okay, so this is the formula you also need to remember or understand basically. Okay, so similarly again we'll do some problem We'll try to solve some problem in this, right? So what the problem says, the question says equal weight of oxygen and methane mixed in a empty container at 25 degrees centigrade. What will be the fraction of the total pressure exerted by O2, right? So try to give it a try, and then you are welcome to see the solution. Okay, right? So let's say both are of equal weight, like equal weight of oxygen and methane are mixed, right? So let's say let x gram of oxygen and methane are mixed, right? So what the question asks that what will be the fraction of the total pressure exerted by O2, right? So they are asking to find PO2, right? PO2 is equal to mole fraction of O2 into total pressure, right? So this is the thing. So now we need to find mole fraction of O2 and total pressure of the system after mixing, right? So if you see that total pressure, like we need to find this in terms of the total pressure only, right? So basically we need to find the mole fraction of O2 for the system, right? So how will find this? Basically simple thing, very simple thing. Like then moles of O2 is how much? That is x upon 32 moles, right? Like moles upon molar mass upon molar mass, and moles of methane is basically x upon 16 moles, right? Moles. So mole fraction of O2 will be equal to what? N of O2 divided by N of O2 plus N of CH4, right? So this is basically N upon 32, x upon 32 divided by x upon 32 plus x upon 16, right? So if I try to solve this, x will cut in all plus, so 32 divided by 1 upon 32 plus 1 upon 16, right? So 1 upon 32 divided by 32, 1 plus 2, so this is basically 1 upon 3. Hence special pressure of O2 will be equal to 1/3 of P, right? So what fraction of, so the question says what will be the fraction of the total pressure exerted by O2. So it will be the 1/3 of the total pressure will be exerted by my O2, right?